Hey everyone, and welcome to This Explainer. Today, we're diving into something absolutely fascinating, a complete visual masterclass study guide for applied robotics. If you're an engineering student or just an aspiring roboticist, you're in the right place. We are going to completely demystify those super complex robotic equations you always see in textbooks and really bridge the gap between all that abstract mathematical theory and real-world applications like robotic exoskeletons. Okay, let's jump right in.
Here's our game plan for today. We'll start with core theory definitions, work through 3 practice problems, decode the Manipulator Jacobian, explore some exoskeleton history, and then we'll wrap up with a high-yield study cheat sheet.
Module 1. Core Robotics Theory Definitions. Before we even touch any matrices or heavy math, we've got to understand the absolute basics. And really, there is a hard, clear line between these two major fields. Kinematics is simply the study of motion without considering forces. It's all about geometry, position, and angles. It's the where and the how. Dynamics, on the other hand, well, that's where things get heavy. Dynamics considers the associated forces and torques. So when you actually factor in mass, gravity, and the literal physical effort required to move a robot arm, you're doing dynamics. You definitely want to keep these neatly categorized in your mind as we move forward.
Module 2. 3 essential practice problems. Let's put that theory to the test.
All right, let's look at problem 1, solving inverse kinematics for a 3-degree of freedom manipulator. Now, don't get bogged down in every single line of math here. The overarching strategy is what's fascinating. We essentially start with this large transformation matrix that represents exactly where we want the robot's hand, its end effector, to go. By comparing elements of this matrix, things like the normal and approach vectors, we can mathematically isolate the exact joint angles we need. By using the arctangent function, we can pinpoint θ1 and θ2. We're basically asking the math, hey, if I want the robot hand right here, exactly how much do I bend joint 1 and joint 2? It's like working backward from your destination.
Moving on to problem 2, we hit the famous Denavit-Hartenberg, or DH parameters. You'll see this everywhere. It's the gold standard for mapping out a robot's geometry. We're working with 4 key variables here: link length, link twist, joint offset, and joint angle. Setting up these parameters is pretty much always step 1 when you're modeling a robot. Once you assign coordinate frames to each joint and measure the distances and angles between them, it's honestly like magic. The rest of the kinematic equations practically write themselves.
For problem 3, we're shifting gears into dynamics, using the Lagrangian formulation. Just imagine a simple 1-degree of freedom pendulum, basically a single-jointed arm. The absolute heart of this is the equation L equals K minus P. K is the kinetic energy of the arm in motion, and P is the potential energy, which is driven by gravity pulling on the arm's mass. By calculating the difference between these two energies and then taking their derivatives, we can figure out the exact amount of torque the motor needs to output just to swing that arm. It is an incredibly elegant way to handle robot physics.
Module 3. Understanding the Manipulator Jacobian.
So what exactly is the Manipulator Jacobian? Simply put, it's a matrix that relates the end effector's linear and angular velocity to the velocities of the robot's individual joints. I like to think of it as a mechanical transmission or maybe a gearbox. It perfectly translates how fast the elbow and shoulder are spinning into how fast the hand is moving in a straight line. It's the ultimate link between joint speed and hand speed.
And here is the actual equation itself. The structure of this thing is just brilliant. On the left, we have the linear and angular velocities of the end effector, and they relate directly to a vector of our joint velocities on the right. Sitting right there in the middle, multiplying them together, is our 6x(n) Jacobian matrix. Why 6x(n)? Well, a robot can have any number of joints, n joints, so the matrix spans 6 rows by n columns. This matrix right here, it's literally the master key for controlling a robot's speed.
Module 4. History of robotic exoskeletons. Let's step away from the abstract math for a second and look at the real world.
The evolution of these machines is just wild. It actually kicks off way back in 1890. Nicholas Jacobian patented this crazy concept using bow leaf springs attached to a person's legs to augment running and jogging. Obviously, purely mechanical. But jump forward to 1999, and you have researchers like Choi applying formal kinematic modeling to 1-degree of freedom systems. By 2004, Yokogawa and Hara are doing these incredibly complex manipulation analyses on the human thumb, just trying to figure out how a machine could possibly replicate it. And then boom, by 2007, things explode in complexity. Kawasaki develops an 18-degree of freedom direct drive robotic hand. We went from literally strapping springs to our legs to building systems that require insanely advanced kinematic matrix math in just over a century.
Module 5. Exoskeleton Force Control Strategies. Because building the exoskeleton is really only half the battle, right?
To actually control the force safely, we rely on a continuous feedback loop. We start with a desired force, basically what the exoskeleton is supposed to be doing. We compare that against the actual force being applied to the human user, which generates an error value. We take that error, pass it through a stiffness matrix, and then, here's the kicker, we multiply it by J-transpose. That is the exact transpose of the Jacobian matrix we just talked about. We are literally taking our velocity math and using it in reverse to figure out exactly how to adjust the joint torques to match the desired force safely. It's mathematical theory directly powering human safety.
And finally, the moment you've been waiting for, the study cheat sheet.
Okay, take a mental screenshot of this, because it's your ultimate map for control systems. On one side, we have the Manipulator Jacobian. We know this acts as our velocity translator. It maps those individual joint speeds to the robot hand's overall trajectory. On the other side, we have sliding mode control. This is a highly robust, nonlinear control strategy. Its entire job is to force the robot state onto a specific, predetermined path, making it super resilient to any unpredictable physical disturbances. Mastering both of these concepts, that gives you complete command over both speed and stability.
Now, before we wrap up, I want to leave you with a pretty provocative thought. We already know researchers are starting to integrate neural data fusion, literally reading brain signals directly from human operators, into these exoskeleton control loops. So as these machines get to the point where they can predict human intent before a muscle even twitches, how are these foundational kinematic and dynamic equations going to need to evolve? How does the math keep up with the actual speed of human thought? It's a fascinating frontier to think about. Thank you so much for hanging out with me on today's Explainer, and I really hope this study guide serves you well on your exams or engineering projects. Keep questioning, keep calculating, and I'll catch you next time.